In this lecture, we're going to talk about portfolio optimization with multiple risky assets. So we're going to take risk and we're going to decompose it into two broad categories. And this is all just very roughly speaking. The first is systematic risk. That's also called market or non-diversifiable risk. So it's called systematic risk because it's common to everything in the system or everything in the market. And as we'll see, this type of risk cannot be diversified away as you build a portfolio. The other kind of risk is idiosyncratic risk, and it's also referred to as firm-specific or non-systematic or diversifiable risk. So it could also be called asset-specific risk. This is risk that is particular to an asset and is not necessarily common to a broad class of assets or to all assets. And as we'll see, it can be diversified away. So let's go through the rough concepts as to why idiosyncratic risk can be eliminated by portfolio diversification. Let's begin with the thought experiment of holding just one asset in our portfolio. Then the portfolio is the asset, and the risk of the portfolio that is equal to the risk of the asset, which is the sum of the asset's systematic and idiosyncratic risks. Now if you add another stock to the portfolio, and those two stocks are perfectly correlated, so that the prices always move at the same time and in the same direction, then you won't have benefited the portfolio risk at all. Every time the price of one stock rises, the price of the other will rise, and the returns will both fall at the same time. And every time one price falls, the other price will fall, and the returns will rise. And so the return risk in your portfolio of the two assets won't be benefited at all by holding multiple assets. It will look exactly the same as the two assets themselves. Now, if the idiosyncratic components of the two assets are uncorrelated, then there's still a portion of their risk that's correlated perfectly, and that's the part that's due to the systematic shock. The shock that hits each of the, or the risky component that hits each of the assets identically will be perfectly correlated. But the idiosyncratic shocks, or the risk that's due to their idiosyncratic nature, those will occur at different times and will have different magnitudes and will not cause the prices to move in lockstep. And so that will cause the overall prices of the assets to move not exactly together. And that will improve the risk characteristics of the portfolio. It will actually reduce the risk, because sometimes when the price of one rises, the price of the other may fall, or it will just stay the same, or not rise as much. And likewise, sometimes when the price of one falls, the price of the other won't necessarily fall, because the idiosyncratic shock may cause it to stay the same or to rise, and hence the overall risk, the volatility of the returns of that portfolio will be smaller. And we'll see this quantitatively, more concretely later in the lecture. And then finally, what if the idiosyncratic components of the two shocks are negatively correlated, that is, perfectly negatively correlated? Well, we know that the systematic shocks are still going to cause them to move together identically. So that portion of the risk is going to be perfectly correlated. But the idiosyncratic shocks is going to cause them to move in opposite directions, so that when one price rises, the other price will fall due to the idiosyncratic shock, and the reverse. And so that's going to reduce the overall risk of the portfolio. Now, as we add more and more assets to the portfolio, that compounds this effect of diversification, only if they're not all perfectly correlated with each other, which is actually a very unlikely thing to find in practice. So in fact, as you add many, many assets to a portfolio, since they're not perfectly correlated, each one reduces the risk characteristics of the portfolio. In theory, it should be possible to eliminate all idiosyncratic risk by increasing the number of assets. Essentially, any shock to one particular asset should get smoothed out or averaged away as you add in many, many, many assets and put in only a very small fraction of your wealth into one little particular asset. That is, this is working under the assumption that as you add many, many assets, that you're also decreasing the amount of weight your portfolio puts on any one asset. Now, systematic risk, that can't be eliminated because as many assets as you add in, they're all exposed to that same systematic risk or same systematic shock. And since they all receive that same shock, there's no way to diversify it away. It will be common not only to all the assets, but because it's common to all the assets, also to your portfolio. So here's a diagram. If there were no systematic risk, the first panel here shows that as you add assets, N on the x-axis shows the number of assets in your portfolio. The y-axis shows the volatility of the portfolio. As N goes to infinity, you see that the volatility of your portfolio should asymptote to 0. You should be able to eliminate all risk. However, in the case where there's market risk or systematic risk, you won't be able to eliminate that portion of the risk. So at that dotted line, you can't get any lower portfolio volatility. So there's an asymptote. As you add assets to your portfolio, it will asymptote down where it eliminates all the diversifiable or idiosyncratic risk and then asymptotes to the market risk level. Let's make this all a little bit more concrete. So let's suppose that you can invest in two risky assets. The first one is going to be a portfolio of debt assets or bonds, and we're going to denote it by D. Note that I'm not saying that this one is a risk-free asset because it could have long-term bonds. Typically we think of the risk-free asset as a type of bond, like a short-term government treasury T-bill. However, this portfolio of bonds could have longer-term bonds, it could have commercial paper, which are bonds issued by companies, and so it's not considered to be a risk-free. It will be a risky portfolio, but less risky than the next asset, which is an equity asset, that is, a portfolio of equity stocks, which we're going to denote by E. So we have portfolios D, debt, and E, equity. And then we will label the fraction of our wealth that we put in asset D as omega sub D. So omega sub D will be a number between 0 and 1, something like 0.2 if we put in 20% of our wealth into the debt asset. And then omega sub E is going to be the fraction of wealth that we put in the equity asset. And we are going to constrain, in general, we are going to constrain portfolio weights so that the weights sum to 1. This is a constraint because it wouldn't have to be the case. I could set omega sub D to 0.2 and omega sub E to 0.2 so that I'm investing 20% of my wealth in each of the two assets. But then I'm only investing a total of 40% of my wealth. Well, here what we're saying is we're going to constrain our weights so that we are investing 100% of our wealth. Whatever we're not investing in D, that is right here, we are investing in E. So that doesn't mean that in reality you're investing all of your wealth. It just means that if you take all of your wealth, W, and decide on some portion, let's say you want to invest 70% of your wealth, then we're going to call that invested wealth, IW. And then this amount of wealth we are now going to treat as the wealth for which everything will be invested. And the omega sub D and the omega sub E are going to be the proportions of this amount that are invested, all of which we know is invested, and hence these must sum to 1. Now we're going to label the returns to portfolios D and E as R sub D and R sub E. And given that those are the returns, then the return of the portfolio, the overall portfolio of these two assets, is going to be the weighted average of these two assets, or these two portfolios of assets. So the return to my overall portfolio P is going to be omega sub D times R sub D, omega sub E times R sub E. You should be comfortable with this since we talked about this in the last lecture. More specifically, if I say that R sub D, the net return, is equal to 0.03, and that R sub E is equal to 0.05, so that the equity asset is paying 5% return, and the debt asset is paying 3% return, then if I put, let's say, 25% of my wealth in the debt asset, omega sub D is equal to 0.25, and omega sub E then is equal to 1 minus omega sub D, which is equal to 0.75. So I'm putting 75% of my wealth in the equity asset. Well, let's say that I've started with $100. If I have $100 that I want to invest, that means that I'm investing 25 in D and $75 in E, clearly. Now what does that mean? What is my overall return going to be? Well, given that I have $25 in D, I know that that's going to be $25 times 1.03 next period. Let's say that these returns are for a month. So if I put my $25 in the debt asset for a month, it's going to turn into $25.75. And then if I put if I put $75 into the equity asset, returning 5%, that's going to be $78.75 at the end of the month. What is my total earnings? Well, it will be, so total at the end of the month equals 25.75 plus 78.75, which is equal to 104.5. Now that, of course, is a 4.5% return because I got $4.05 on my initial $100. But note, 4.5, if I come and make a new slide, then 4.5, if I say the weighted average of the two returns, it turns out 4.5 is just the weighted average of those two returns. So that I put 0.25 times let's just say 0.03 plus 0.75 times 0.05. Well, that's equal to 0.0075, that's what this is, plus 0.0375, which is that. Adding those two together, we get 0.045. So the alternative way to look at it is I'm taking $100, some fraction of that, and I'm investing it into 3% return. Plus $100, some fraction of that, which I'm putting into a 1.5% return. 1.05, sorry. And so it turns out, if I factor out the 100s, that's equal to 1.03 times omega d plus 1.05 times 1 minus omega d, or omega sub e, which is just the weighted average of the two returns. So it turns out that we can also take out the 1's, so that we have 100 times 1 plus 0.03 omega d plus 1 plus 0.05, that should be 0.05, I'm just going to call it omega e now, just for simplicity. I can distribute the omegas into each of these sums, so that that's equal to 100 times omega d plus omega d times 0.03 plus omega e plus omega e times 0.05. Now what do we notice? These two, we're adding them together, and by the constraint, those two sum to 1. So that we have 100 times 1 plus omega d 0.03 plus omega e 0.05. And guess what? We have 100 plus 1 times 1 plus, and this is the net return to the portfolio, R sub p, which is the weighted average of the two net returns right here. So that should convince you that, in fact, the return to the portfolio, that when I invest my money in a weighted sense into these two assets, D and E, the net return on my money should be just a weighted average of those two returns. Now, by the properties of expectations, we know that if this is the relationship, if the portfolio return is the weighted average of the two returns, well, you should also be comfortable from the last lecture with the fact that the expected return to the portfolio then is just the expected return, the weighted average of the expected returns. That is, all I'm doing is putting an expectation around here on both sides, and then we know that the expectation can go through to each component, and I can pull out the weights since those are constant. Likewise, by the properties of variance, you should be comfortable now with the fact that the variance of a sum of random variables, so here we just have a random variable that's a weighted sum of two other random variables. Well, the variance of that random variable is the coefficient squared times the variances added together, plus any cross product variances, covariances, times 2. Now, it's often useful to express variance and covariance in matrix form. So what we do is we put the variances on the diagonal and the covariances on the off-diagonal, so that these off-diagonal components are actually, so sigma d e is equal to cov of the return to d with the return to e. And sigma ed is equal to cov of the return with e of e with the return to d. Now, the definition of covariance, which just says, let's write the definition of the first one, of this one. Well, that's just the expectation of RD minus its mean times RE minus its mean. What's the definition of this one now? Well, that's just the expectation of RE minus its mean times RD minus its mean. But notice, these are just two things that are multiplied together. So there's no reason I can't just swap them, so that I can say that's equal to writing this one first and then this one. RE minus mu E, RD minus mu D. So that in fact, these two are equal. Or, all I'm saying is that these two components, sigma DE and sigma ED, those are identical numbers. The covariance of D with E is also the covariance of E with D. And so this covariance matrix is always going to be symmetric. Anytime you have a component that summarizes the covariance between D and E, then the component matching it on the other side of the matrix is going to be identical because it just swaps the order, which is exactly what this is saying here. Now, this capital sigma here, it's often referred to as a covariance matrix. Some people refer to it as a variance covariance matrix. Now, this covariance matrix, it can be generalized to multiple assets. So you could have, let's say, 4 assets, sigma 1 squared, and then sigma 1, 2, sigma 1, 3, sigma 1, 4. Those are the covariances between 1 and 2, and 1 and 3, and 1 and 4. And then sigma 2, 1, sigma 2, 2, well, sigma 2 squared I'll call it, sigma 3, 1, sigma 2, 3, and then sigma, we should probably erase that for clarity, sigma 2, 3, and then sigma 2 with 4. I'll go ahead and put the bracket out here already. And then you have sigma 3, 1, the covariance of 3 with 1, covariance of 3 with 2, variance of sigma 3, and then sigma 3, 4. Finally, sigma 4, 1, sigma 4, 2, sigma 4, 3, and the variance of 4. So these terms are the diagonal components. Those are the variances. And then note, sigma 1, 2 is the same as sigma 2, 1. Sigma 1, 3 is the same as sigma 3, 1. Sigma 1, 4 is the same as sigma 4, 1. So every component above the diagonal, up here on this region, will have an identical component below the diagonal. And in fact, this matrix is a mirror image of itself over that line. That is, if you flip the matrix in this direction over that line, it will flip right onto itself and be the exact same matrix. That's known as a symmetric matrix. So this is a symmetric matrix. A covariance matrix is always symmetric. And in fact, I like to call it a covariance matrix because although these are variances, I can think of these variances, I can think of sigma 1 squared as just sigma 1, 1, and sigma 2 squared as sigma 2, 2. Because recall from previous lectures that the variance of an asset is just the covariance of it with itself. So that sigma 3 squared is equal to sigma 3, 3. And so in fact, I call it a covariance matrix because even though these are variances right here on the diagonal, I just think of them all as covariances so that every position is the covariance. And in fact, it's just summarizing the covariance of each asset with each other asset, including itself. And so as I've already noted, the diagonal terms represent variances, and the off-diagonal terms represent covariances. Now it's often going to be useful to us to summarize the co-movement of two assets with the correlation rather than the covariance. So let's recall that the correlation between two assets, which I'm going to denote rho sub xy for the correlation between x and y, is by definition the covariance of those two assets divided by their standard deviations. So now if we just manipulate this equation by taking these standard deviations over to the other side, we see that the covariance is equal to the correlation of the two assets times the standard deviations. And it's important to recall that if you work through the math over here, that the correlation is mathematically constrained to lie between the numbers -1 and 1. Now the previous relationship for the variance, the portfolio variance that we wrote, allows us to rewrite it as this. So remember, before we wrote that it was equal to this plus this, and then we had 2 times omega d, omega e, and then we had cov r d with re. Well, now what we're doing is we're substituting what we just did on the previous slide, and we're saying that's equal to rho sub de times sigma d sigma e, which is how we get to this last term right here. So now instead of writing it as a function of the covariance, we're writing the overall portfolio variance as a weighted average, well, as a sum of the weights squared times the variances plus 2 times the weights times the correlation times the standard deviations. Now, since the correlation must lie between -1 and 1, we know that the portfolio variance is greatest when rho is equal to 1, right here. So why is this the case? It actually would be possible for the case of rho equal to 1 to cause a smaller variance than some other rho if any one of these values up here were negative. But in fact, we know that standard deviations are always positive, and we are going to constrain these numbers to always be positive. And so this whole number, which is just a multiplication of all positive numbers except for possibly rho, which could be negative. Remember, rho could fall below 0 between -1 and 0. Everything else in that multiplication is positive. So in that case, we know that this number over here is biggest when rho is equal to 1. Anything less than that, well, we can actually just write out. Think of that number as this. This number, sigma d, sigma e, which is all a positive number so far because everything here is a positive number individually. And then we multiply that whole number by this rho that I have, rho de. Now it's biggest when rho is equal to 1 because otherwise I'm taking some fraction of that number if rho is less than 1. And if rho is in fact negative, then I'm making this number negative, which in fact further reduces the portfolio variance. Now there's some special cases that are important to note. When rho is equal to 1, then in fact we take that out because it's just a 1. Then we can rewrite the portfolio variance as the square of the sum of the two volatilities, the weighted average of the two volatilities. If you actually multiply this out, you'll see that that's equal to omega d squared sigma d squared plus omega e squared sigma e squared plus omega d, omega e, sigma d, sigma e, and they're two cross products, so times 2, which is exactly what that term is because we've taken out the rho, which is equal to 1. Which means that if we take the square root of this side and of this side, we just eliminate these two values, and you see that in this special case, only when rho is equal to 1, we get that the volatility, not the variance, but the standard deviation of the portfolio is a weighted average of standard deviations. That's a very interesting case. So note that we do not have any extra terms out here that deal with covariances. So this is exactly what I just said, that in this very special case, the portfolio volatility is equal to the weighted average of individual asset volatilities. And because we know the variance is biggest when rho equals 1, we know that the maximum possible portfolio standard deviation is just the weighted average of portfolio standard deviations. And that for any other rho, that it's going to be lower than that, because let's just recap the steps. When rho equals 1, that's when sigma p is the greatest, and also that's when sigma p is equal to the weighted average of the volatilities. Any other rho less than 1 is going to cause sigma p to be smaller, which means it will be smaller than this weighted average. And hence, the weighted average is an upper bound for the portfolio volatility. The portfolio volatility will never be greater than that and will most likely be smaller than that. So, what have we learned? We know that the expected return of the portfolio is always the weighted average of the individual expected returns. And we know that the portfolio volatility is the weighted average if rho is equal to 1 only. But otherwise, it's less than the weighted average of the individual volatilities when rho is not equal to 1. And so what does that mean? The portfolio is actually, it has a weighted average of returns, but less than a weighted average of volatility, so that the volatility characteristics are better relative to the return, in which case we say the risk-return properties of the portfolio are better because it's maintaining an exact weighted average of returns, but less than a weighted average of volatility. Recall that one way to characterize the return to volatility characteristics is by the Sharpe ratio. So if we write the Sharpe ratio of an asset, so the Sharpe ratio of the E asset might be mu E over sigma E. Well, what we're saying is the Sharpe ratio of the portfolio, well, that's just equal to a weighted average of the individual assets, but sigma p is less than a weighted average. So that's equal to the weighted average of D with E, but this is less than the weighted average of sigma D plus E sigma E. And so the Sharpe ratio of the portfolio, since this goes down, the whole Sharpe ratio should be going up. The Sharpe ratio of the portfolio should in fact be higher than the Sharpe ratios of each of the assets. Now, as I noted before, portfolio variance is made smaller as we reduce the correlation. In fact, if we set rho equal to -1, then it turns out you can factor the expression for the portfolio variance as this. I won't do it here, but go ahead and just multiply out, expand this quadratic here, and you'll see that you'll get exactly the the variance expression that we had above with rho equal to -1. And then there's an error here in the slides. There should not be this parenthesis and that 2. But if we take the square root of both of these, well, then we have the volatility on the left-hand side, and on the right-hand side, we have just the difference between these two, but it must be the absolute value of the difference, because square roots always yield positive numbers, whereas it would be possible for omega E sigma E to be larger than omega D sigma D, yielding a negative number. The square root of that difference must yield the positive value of that number. Now it turns out if you select omega sub D to be equal to this number, so that don't get shaken up by the fact that it's a ratio of volatilities. In fact, omega sub d is just some number dictated by these two numbers, that in that case, when rho is equal to -1, sigma p will be equal to 0. And we can compute that. We can actually compute using this expression, and again, remember, we need to eliminate those two things right there. We can actually compute what the value is. So in this case, we will say sigma p is equal to omega d, which I'm saying is sigma e all over sigma e plus sigma d, times sigma d, minus omega e, which is going to be 1 minus sigma e all over sigma e plus sigma d, times sigma e. Then we just start performing algebra. We say that's equal to sigma e, sigma d, that's a times now, all over sigma e plus sigma d, minus, now we can distribute this to be sigma e, and then the minus here is a plus sigma e squared all over sigma e plus sigma d. Now in order to group everything, I need to write this with the same denominator as the others. So what is that equal to? Well, we'll have to make a new slide here. So where are we at? Sigma e times sigma d all over sigma e plus sigma d minus sigma e plus sigma e squared all divided by sigma e plus sigma d. Well, if we want to write this term with a common denominator, we first write the first term minus sigma e times sigma e plus sigma d all over sigma e plus sigma d, and then plus the final term. We need to distribute that into each of these, and then we can group everything together into one numerator, so that what we have is sigma e times sigma d minus this first portion, sigma e squared, minus sigma e sigma d, which is what that is right there, and then finally plus this guy right here, sigma e squared, all over one denominator, sigma e plus sigma d. So what do we have? That cancels that cancels that. That is 0 over sigma e plus sigma d, which is 0. Remember, all of this was sigma p squared. So now we have just said, we've shown that when omega d is equal to this value, sigma e all over sigma e plus sigma d, then in fact, if you plug in and do all the math, you will achieve a portfolio variance of 0. This shouldn't disturb you that I'm calling the weight that. I'm just saying that if you know that sigma e is equal to, let's say, 0.0 or 0.1, and you know that let's say that that's equal to 0.2, and that sigma d is equal to 0.1, so that sigma e has 20% volatility and sigma d has 10% volatility, then all I'm saying is that you're in a situation where you're doing this computation, which is equal to 0.2 over 0.3, which is just equal to 2/3, so that you're putting 2/3 of your wealth into D and 1/3 into asset E. So that in this case, because I'm saying omega D is equal to sigma E all over sigma E plus sigma D, I know that this is always going to be a number between 0 and 1 because the numerator never goes below 0 and it will never be greater than those values because I'm taking the number itself divided by the number itself plus some other number, and that's a D even though it looks like an A. So that this number in the numerator is always smaller than that number in the denominator. So it can't be greater than 1. So I know that this omega D is bounded between 0 and 1. So this is all just a very long way of saying that in this special case, when rho is equal to -1, that is when the two assets, D and E, are perfectly negatively correlated, that you can find a weight so that your portfolio has 0 variance or 0 volatility. That doesn't mean that any weight will do. You can't just form any portfolio of those two assets. And once again, I'm going to scratch these typos out. But you can form a portfolio. There does exist a portfolio that has that exact weight, such that only when you have negative correlation do you get 0 variance. So here's a graphical representation of some of the calculations we've been doing. So on the one axis, we have standard deviation. And on the other axis, we have expected return. And what we're doing here is we're saying, suppose we have asset D and asset E. Asset D has that standard deviation and that expected return. So 12% standard deviation, 8% expected return. That's a mu of 8% for D. And E has a 20% standard deviation and a 13% expected return. Then as we choose omega, we are going to be forming portfolios that are combinations of these two portfolios. And it turns out that the possible set of portfolios that you can choose when you vary omega, in the case of rho equals 1, is this straight line. Recall that in the case of rho equals to 1, that the expected return of your portfolio is the simple weighted average of the two expected returns here and here. And that when rho is equal to 1, the standard deviation is also the weighted average. So this line represents the weighted averages of standard deviations and expected returns between those two portfolios, which is exactly why it's a straight line. So if rho is equal to 1 and omega is very, very small, then I'm creating some portfolio right here in that line that's a weighted average of that standard deviation and that standard deviation and also a weighted average of those returns. And it will end up right there. And then the line will continue on up as I increase my omega, putting more and more of my wealth in asset E until I've put almost all of my wealth, and then I reach actually by asset E by putting all of my wealth in it. Now it turns out that when rho is not equal to 1, this relationship is not linear. In fact, there's this nonlinear relationship. If you actually were to map out, you could start with a whole sequence of values of omega, starting with very small omegas at close to 0, and then omegas rising up to 1. You'll find that if you map out the standard deviations and the expected returns of the portfolio, now taking into account that the standard deviation is not a weighted average because rho is not equal to 1 over here, but that the expected return is still the weighted average because it's always the weighted average, then you'll find that the map looks like this, that there's this weird bow, and that the relationship is not linear. And you'll find that as you decrease rho, that bow becomes more pronounced, and if you decreased it below 0, you would find these big bows that map out the set of possible portfolios as you vary omega. And that in fact, when rho is equal to -1, that bow becomes this sharp angle, and it takes the possible portfolios all the way, it takes one of the portfolios all the way down to 0, which in fact is that portfolio we said, if omega, so here would be small omega, right? And as omega got bigger and bigger and bigger, you would eventually hit a value where the portfolio variance is 0. But then as you increased omega closer to 1, you would come all the way back up to here. Well, the value, recall, that sets the portfolio variance to 0 is the special case, sigma e over sigma e plus sigma d. So those curves that we just plotted, we call those portfolio opportunity sets, or portfolio frontiers. Now, since individuals prefer less risk and greater return, at least that's the assumption we're making in this course, we know that frontiers that are bowed to the northwest, remember we had pictures that looked like this, portfolios that are bowed out this way are better because we prefer portfolios that have smaller standard deviation and greater expected return. So we like portfolios in that direction, as we explained, as we investigated in the last lecture. So clearly, we prefer those frontiers for smaller values of sigma, or of rho. Recall that when rho was 1, we had a frontier that looked like that. When rho was 0.3, we had a frontier that looked like that. When rho was 0, well, we prefer these later frontiers to these ones, the ones that correspond to smaller rho, because they give us the opportunity to get sets, portfolios, that is, of assets that are further in that direction. So now let's move on to building portfolios of 3 assets, and this is actually not going to be much more difficult. So we're going to put our money into 2 risky assets like we were just talking about, and then the third asset is going to be a risk-free asset, so that we're going to combine these portfolios that we've just been talking about of 2 risky assets with a third asset that's risk-free. So now the portfolio frontier is going to consist of all the curved risky frontiers. I'm going to call it a risky frontier, that curved frontier, those curved frontiers that we were just looking at in the picture. So our frontier, the overall frontier, will now consist of those curved frontiers between the 2 risky assets, as well as every possible capital allocation line connecting the risk-free to any portfolio on the risky frontier. And we know that we prefer high Sharpe ratios. And since, as we talked in the last lecture, since the slope of the capital allocation line is in fact the Sharpe ratio, we want a very steep cal because we also want a very steep Sharpe ratio. So here's the picture. The curved frontier is just the frontier that arises by only investing in D and E, the 2 risky assets. And the curved frontier is arising because we're assuming that there's some correlation, rho, D, and E, that's less than 1, which is why the frontier, the blue line, is curved. So if we could only invest in D and E, that would be the set of possibilities, set of portfolios we could invest in. And that arises by varying omega. Now, the frontier could extend beyond D and beyond E if you allow for omega to be negative, which would be a special case where you allow short selling and then over-investing in the other asset, potentially. But we're not going to think about short selling right now, so let's only consider the frontier between D and E itself. Now, as I said, if we could only invest in D and E, this line right here would be the set of possible portfolios for us. But now if we throw in a risk-free asset that returns some return like 5%, then you can invest a portion of your portfolio. Let's say you designate 70% of your portfolio to be in one of these portfolios right here, and then the remainder goes into the risk-free. Well, then you're just creating a capital allocation line that connects this with that. Recall in the last lecture, what we did is we built portfolios of a risk-free, and some other asset, and then just drew the straight line between them as being the set of possibilities that you can invest in. Well, now we're saying make your choice between any portfolio here and this asset, where that portfolio here is also a combination of those two. And so we could pick any portfolio. As you see here, this A and this B are portfolios on the risky frontier. Well, the overall frontier then becomes the line, the cal, connecting the risk-free to whatever portfolio you choose on the risky frontier. And there are a potentially infinite number of cals, because note, there are an infinite number of portfolios on this frontier and a cal connecting every one of them. So there are actually a whole lot of capital allocation lines that you could choose. Now, which capital allocation line do you want? Well, as I mentioned on the previous slide, you want the one with the steepest slope, because that represents the highest Sharpe ratio. So that's exactly what that is saying right there. The slope of the cal is the Sharpe ratio of whatever asset it connects to on that risky frontier. So that means that the investor wants to solve this problem. Maximize the Sharpe ratio by choosing some value of omega. The Sharpe ratio being the expected return of the portfolio in excess of the risk-free all over the standard deviation. Now this maximization problem has two constraints. Mu sub p must be the weighted average of the two component asset returns, and sigma sub p must be the square root of this sum right here, where I've taken into account, this is actually a typo right here. There should be a squared right there. So that in fact, the portfolio volatility is just subject to this same equation we've been looking at all along. So just to recap, because the investor wants to find the portfolio with the steepest cal, or the highest Sharpe ratio, the investor then maximizes Sharpe ratio subject to the constraints that the mean and the volatility are equal to those weighted averages and average plus covariance or correlation term. Now, to solve the problem, what do we do? First of all, we can substitute the constraints into the objective function. Next, we take the derivative with respect to omega sub d, and we set that derivative equal to 0. And then we perform a bunch of tedious algebra rearranging things to solve for omega sub d. And in the end, we get to this solution. I won't make you solve it. But the solution is, and I've put a star on omega because it's the optimal omega that I found by setting that derivative equal to 0. Well, it turns out that is equal to this quantity right here, where Rp sub d and Rp sub e are the risk premia. That is, Rp sub e is equal to mu e minus Rf, and Rp sub d is equal to mu d minus Rf. I've simply substituted so that I don't have a lot of tedious notation, so I've just simplified the notation by calling these Rp's as well as down here. And so what we have is this expression where we can solve if all we know is rho, sigma d, sigma e, mu d, mu e, and Rf, that is the expected returns, the volatilities, the risk-free rate, and the correlation. If we know all those values, we can compute the optimal omega. Graphically, what is that going to look like? Actually, before I get ahead of myself, I should note that the optimal portfolio we're going to call the tangency portfolio, or denote it by T. Now let's look at the graph. What this is saying is that, recall, I can choose any cal that connects to a portfolio here. but I want a high Sharpe ratio for my portfolio. That is, I want a lot of expected return for each unit of variance, which means I want a high Sharpe ratio. But I can't have a cal that's out here because there's no portfolio available to me out here. I must have portfolios on the risky frontier. So the portfolio with the steepest cal is actually the portfolio where the cal is just tangent to the risky frontier. Here in the picture it's called portfolio P. I'm usually going to call it portfolio T. That is the tangency portfolio. Any portfolio with a cal that's not the tangency portfolio is actually going to have a more shallow cal and hence a smaller Sharpe ratio, which I do not prefer. Now the optimal cal is the investor's efficient choice set because it offers minimal variance portfolios for every choice of expected return. So that is to say that I can just invest in these assets, or I can just invest in portfolios here. But why do I prefer to invest in? So what I can do is I can synthesize a tangency portfolio here, and then I can form some portfolio between the risk-free and the tangency portfolio somewhere on this line. I can choose a portfolio here. Why do I prefer that? Because for any expected return, I've got a smaller variance here than I do here. And so if I make this plot bigger actually, let me just erase this one and make this a bigger plot so that it's a little bit more clear. If I have D and I have E in some frontier here, and here's the tangency portfolio. So this is D, that's E, and that's T, where this is portfolio F, the risk-free, so that the tangency goes right through here. Then for any given, remember, this axis is expected return and this is volatility. Well, for any given level of expected return, a portfolio here has smaller variance than a portfolio here. That is, a portfolio on the cal has smaller variance than a portfolio on the risky frontier. And the same here. I can just send dotted lines through, and for any expected return that I choose, I'm always going to have a smaller variance on the cal than on the risky frontier. And so what I'd rather do is, rather than putting all of my investment into some mixture of these two and getting a portfolio even P here, what I'll do is I'll say I'm going to put 70% into portfolio P, which is going to dictate weights for each of these, and then 30% I'll put in the risk-free, and that's going to make a mix on this line somewhere over here. That is, put an X right there. That's a mix of that portfolio and F. And so this, the cal that's tangent to the risky frontier, is now my optimal choice set. Now note that I've said nothing about what the investor will actually consume. So far, all I've noted are what the possible choices of portfolios are, not which will be chosen. So what we have to do is actually combine that optimal cal with a specification of preferences, that is within difference curves, to get an idea of what portfolio the agent would actually choose. And so the portfolio choice problem with 3 assets now reduces to simply choosing between one risky asset, which is the tangency portfolio, and the risk-free asset. So if we draw the picture again, now we've got this D and E and some risky frontier connecting them. Then we've got some F, that's E and this is F, and we have a cal. Well, this is now the frontier, the efficient frontier of portfolios. And if we specify preferences, that will, actually maybe I don't want to draw my indifference curve like that. That will give us some indifference curves that might give us a tangency right here. Or that indifference curve might give us a tangency here. And then that will dictate which portfolio on the cal gets chosen. But we have to have a specification of utility which gives us these indifference curves before we can solve that problem. So let's assume, as in the last lecture, agents have this utility function that expected return enters positively and volatility enters negatively, and that gamma is some measure of risk aversion where gamma is a positive number. Well, if you recall that when you allocate between some risky asset P and a risk-free asset F, we're going to call now the optimal portfolio weight tau. Going back to the last lecture, if you remind yourself of how we solve that problem, you'll see that the optimal weight between a risky portfolio and a risk-free asset is just the Sharpe ratio, well, the expected return, that is the risk premium, over gamma times the variance, which is also equal to, remember, the Sharpe ratio of the portfolio over gamma sigma p, because one of the sigma p's is reserved for the Sharpe ratio calculation, and the other sigma p will stay in the denominator with gamma. So if that risky portfolio is no longer just some portfolio P, but is now the portfolio P, then that weight tau, the optimal weight between the tangency and the risk-free, is going to be the risk premium of the tangency portfolio divided by gamma times the volatility, or sorry, the variance of the tangency portfolio. And then given that you're investing that much in the tangency portfolio, you then have to take that much money and divide it according to omega sub d, which dictates how much of this money goes into D and E. So that the weight, now I'm going to call, we need to be very clear here, omega sub d is the fraction of the wealth invested in the tangency portfolio that goes to asset D. And omega 1 minus omega sub d is the fraction of wealth that goes into E. WD is the total wealth. So what I'm saying is, let's say that you have $100 to invest, and that tau is going to be 80%. So you're going to take $80 and put it into the tangency portfolio. Then omega sub d right here tells you what fraction of the 80 you're going to put into D. And 1 minus omega sub d says what fraction of the 80 you're going to put in asset E. So if omega sub d were, and this is a star because it's optimal, were 0.25, and that means of the $80 you put into the tangency portfolio, 25%, or 20 of the 80, is going to go, so we're saying $20 goes into asset D. And the remaining $60, or 75% of that 80, is going to go into asset, actually I should have an arrow here, is going to go into asset E. But then you still have 20%, or $20, that's going into asset F. And that's dictated by 1 minus tau. Everything that you're not investing in the tangency is going into the risk-free. So how did I get to the overall? Overall, so remember, of the $80, I'm putting 20 or 25% into D. But of my overall wealth, that 20 is not 25%, it's 1/5. And of my overall wealth, I'm not putting 75% of my money into E, but I'm putting 60%. So the W sub D and W sub E are computing the overall portion of my wealth that goes into D and E, including the money that is going to end up, that is factoring into consideration the amount of money that goes into the risk-free portfolio. And so all I've done is to compute those numbers as I say how much, what fraction is going into the tangency portfolio, say 80%, times whatever portion of that is going into D, and then whatever portion is going into the tangency times whatever portion is going into D. That will yield the overall portions of my wealth going into those two assets.